and Vlad, thank you for this introduction. Super happy to be here and present to you. I'm Ekaterina. I am a data scientist at NVIDIA. And in my role as a data scientist, my task is to solve various problems of various customers and partners. And as Vlad has mentioned, I do solve problems on embedded devices, making your inferences running faster, sometimes in real time. And embedded devices, what are embedded devices? Embedded devices are robots or tiny instruments you hold in your hands. Today, I will tell you how you can basically enable your robots and embedded devices by means of synthetic data. I got really fascinated by the topic of synthetic data a while ago, and I think it's a very, very good enabler and actually a door opener for things like general AI. So let's dive deep and see what is synthetic data and how it can be helpful. Let's first take a look at this video, and here I'm showing you different robotics applications developed on NVIDIA platforms, NVIDIA hardware and software, and by NVIDIA partners. So in this video I'm showing you, you can see that we can have different robots of different sizes, having different sensors like cameras, lidars, radars. These robots can have different functionalities. They are delivery robots, healthcare robots, like robots who perform surgeries, robots flying to space or doing some interesting stuff with plants, as you see here. In short, robots are, they are large helpers, and they make our lives better. But sometimes robots fail. So imagine you have a rescue robot, and you want this robot to come and help you to solve some problems. But then things like that happen. Oops. Or you have a robot which is supposed to serve you a cup of freshly brewed coffee, but then things like that happen. Oh, here's my favorite one, a robot to serve you ketchup. What can possibly go wrong? And this one is especially painful for me because it's my own vacuum cleaning robot. Happened a couple of weeks ago. Really painful when they fail. Why do robots fail? The reason these robots fail is often because these robots are simply automated robots. And they are not fully autonomous. And what do you understand by automated robots? It's usually some developer who stands behind, who wrote thousands and thousands of lines of code saying, go straight, go to the left. There are some if conditions or loops which guide the robot and tell the robot what to do in some situations. But that's not what we want. We want robots to be fully autonomous. And by saying autonomous, basically we mean that robots will act and react to the environments on their own. They'll make decisions based on the environments they see. Are there any obstacles on the way? Is something preventing me to do this action? And basically, we believe that to enable fully autonomous robots, we need to rely on AI. So what do actually AI robots need? Let's take it at AI robots have many needs. And the first and, the biggest need is data. Data is, digital words. They run on data. Data is the fuel of digital words. And anything related to AI, you need a lot of data. Of course, you need a lot of training. And by training, we understand powerful models, algorithms to train your models, frameworks, all kinds of infrastructure. Again, we also mean hardware. You need a lot of hardware, GPUs in the ideal scenario. So you need a lot to train your robots, your models for robots. And you also need testing. Don't forget testing. You need to make sure that your robots generalize in the real environment. So wherever you trained your robot, you need to make sure that whenever you bring the robot in the real world, it doesn't kill people or doesn't create any additional mess. So you need to test the robot. You need to make sure that the robot generalizes. In my talk, as you may have guessed, my focus will be data. And how do you actually solve the problem of data? And the first thing which comes to mind is just go outside and collect a lot of data, create large data sets, but this comes with a problem. You need to label this data. And again, you can go to services like Mechanical Turk. You can hire an army of labelers who will take your data, draw bounding boxes there, but it's not always feasible. Again, you can also apply techniques like data augmentation, meaning that you take your existing data set and you extend it by applying some simple computer vision techniques. Well, I'm mostly talking about vision and perception systems, so all my examples I'm giving are associated with vision data. So you can apply like flipping transformation, scaling, zooming out. This might help, but then still you remain within the space of your data set, and you still carry the biases of your existing real data set. And as you may have guessed, synthetic data can help to solve these problems. So let's learn actually about the limitations of real data before I start with synthetic data. I mentioned labeling, manual labeling, and that's usually a lot of work. And think of tasks like image segmentation. Like those of you who have ever tried to segment images know that it's a tedious task. Sometimes your hands are shaking, or there are just too many objects to label there, right? And when we're talking about like LiDAR point clouds, it's even impossible to manually segment these kinds of data. So it's very tedious and hard for a human observer. The second limitation, well, these images I'm showing are actually images from our own NVIDIA data set, which we've collected to train our autonomous vehicles. And these are categories of really hard examples which are hard to deal with. The images can be dark, blurry, or hazy. That's also hard to label, right? The objects can be occluded, so you can see a portion of objects which a human observer might even not notice when labeling this data. Some scenes are highly irregular, and you don't know what to expect from these scenes. And whereas other scenes have like high quantity of labels, meaning like you have 1,000 humans in the scene, and it's really also tedious to label it. The next limitation is that, well, sometimes it's even not only tedious, but also impossible to label this data. Think of an example of long-tail anomalies. So what do we understand by long-tail anomalies? Let me give you an example. So you have an autonomous vehicle which is arriving on the traffic light. And the signal is green, so apparently our autonomous vehicle is allowed to drive. But then an emergency vehicle comes from the right, and we need to let this emergency vehicle pass. This is a rare event, and if you want to train a model specifically for this event, it's hard to get grasp of data like that. So we usually call these events long-tail anomalies, the events which are hard to come by with. Again, I mentioned LiDAR data and segmentation of LiDAR point clouds. This is the data coming from non-visual sensors, and it's also really hard and impossible to label. And there are also indirect features like speed and direction. Think of it as a human labeler. How would you label these characteristics? There is no way to know that. So this is the real data which is impossible to label. Furthermore, real data has large amortization costs, meaning that environments change quite often. And in terms of factory, assembly lines get frequently reconfigured. In warehouses, the navigation routes for robots, they often change. Like we can put pallets or boxes there, and robots need to be able to cope with that. So you won't go to the warehouse and try to collect new real data for every layout change. And in retail, packages of products change quite frequently. So think of Christmas, football games, the packages, they kind of reflect the events happening, and you also don't want to constantly go and photograph all these new packages. So synthetic data, as I said, may help to bridge these gaps of real data. So let's go through the benefits of synthetic data. But first, actually, what is synthetic data? What do we understand by synthetic data? The definition I've put here is that synthetic data is annotated information that computer simulations or algorithms generate as an alternative to real-world data. So the key takeaway from this is that synthetic data is generated on virtual world, not in the real world. And synthetic data is fake data, so you will not find this data in the real world. It's fake. And here I'm showing you an example of synthetic data of a warehouse generated in NVIDIA Isaac platform. I'll come to that a little bit later, with the corresponding labels for all kinds of sensors. So you have bounded boxes for objects of interest, you have depth information, and so on and so on. So this is what we understand by synthetic data. And synthetic data comes with associated benefits, as I mentioned. So first of all, synthetic data allows you to create labels where human observers, human labelers cannot do that. Think of things like occlusion, velocity, depth. Now it's all possible with synthetic data. You can simulate adverse weather conditions, and no matter what, you will get your labels there. Synthetic data allows you programmability, and by that we understand that you, as an engineer of synthetic data, you have the full control on your data set. Those of you who have experience with Kitty dataset, a popular dataset for detection tasks in autonomous driving, you know that this dataset lacks cyclists. So there are many cars, there are pedestrians, but there are fewer cyclists, meaning that if you train the models on this dataset, it gets kind of biased against cyclists, and this is an underrepresented class. With synthetic data, you have the full advantage to have, your distribution under control. And if you see that some class is underrepresented, you can easily add more examples of this class by tweaking a single parameter. Synthetic data also allows you faster deployment and development, so you can iterate faster, you can try different scenarios faster, and you can start developing just from the day zero. So with synthetic data, you don't need to go outside, collect real data, and usually real data collection, it costs you a lot of time, and again, your time is collecting the data, but also time of labelers, so that's a long process, creating a data set which is generalizable, which makes your models generalizable on real data. Cost. Also, synthetic data helps you to save money, because collecting the data, you don't spend these weeks on collecting real data, you don't have to pay for the labelers. You simply need, a couple of hours of a GPU and developer time to basically develop your synthetic data initially, but then it pays back. And so it's quick and it's cheap compared to real data collection. Synthetic data allows you higher accuracy. And again, when talking about real data, and when we are relying on human labelers, we know that as humans, we make errors, and it's hard to draw a precise bounding box sometimes, or segmentation mask. But with synthetic data, your ground truth is always perfect, always 100% perfect. So no human errors in the loop. Synthetic data allows you to address corner cases, things like long-tail anomalies. Another cool example could be, not very cool, if the robot destroys your warehouse. You want to prevent it, so you don't want to create real situations like that. But you can easily generated well, you can build a digital twin of your warehouse, and then you can put your robot and do all kinds of distraction there and get the data from it to train your model on. So, corner cases. Last but not least, synthetic data frees you from data restrictions. Those of you who work with public data sets and use this model in production, you know that sometimes public data sets come with some legal restrictions. Sometimes you need to, well, pay for the maintainer of the data set, or if you use a model pre-trained on such a data set, you also need to consider that. With your proprietary synthetic data, you're free of that. Also, another thing, real data needs to be anonymized, and we want to make sure that the data in the real data is not identifiable. This is a very, very big problem in healthcare, for example, where we use patient data. So we need to be really cautious with privacy, and synthetic data helps you with that. So now I think I kind of managed to convince you, hopefully, that synthetic data is good. So let's see how deep learning with synthetic data works. But first, let's see how typical deep learning works, just for a comparison. In typical deep learning, you collect thousands of images of, in this example, cats and dogs. The labelers draw bounding boxes or segmentation masks around the objects. Then you convert your images in the format acceptable by your model. For example, you know that there are formats like Kitty, Coco, and depending on what kind of model you have from which framework, you might need to adjust your labels to this format. Then you run the training itself, and then you evaluate the model. And based on that, you decide, OK, shall I tweak my hyperparameters? And, well, you try different hyperparameters. If you're happy with your model, then it's good. But if something does not work, you may try different architectures. And you also may need to collect additional data if you see that your data set is not representative enough. With synthetic data, it can be done differently. So first of all, you need to decide on what kind of content I need to generate. Then you need to basically have the set of the components like contextual scene synthesizer, so you need to synthesize the scene. You need domain randomizers, and we'll come to that in a few seconds. And you need to render your scene. So having all these things are parameterizable, so you can have some hyperparameters to tweak these operations. You can create your synthetic data set. Then you can use the synthetic data set to train your model, well, same way you train with real data. And then you evaluate your model. And typically, when we want to evaluate the synthetic data set, we fix the model, we fix the parameters as it is, and just apply some variations to the data set and see how does it make our model perform in evaluation. And we can have it as a closed feedback loop where the evaluation guides you and you can tweak the parameters of these renderers and generators to have the model which works well and to have the data set which will also be good for all kinds of model. You can go further and you can say, OK, this is the data set I'm really happy with. And then you can fix the data set and you can try different models and see how different models perform on this very data set. It also helps you to see if the data set is good or not. So this is training with synthetic data. But the very important thing to take care of when training with synthetic data, and you need to be aware of this, is called sim-to-real domain gap. What is domain gap? So think of it as a difference between the real world and your synthetic data. It can be also applied to, well, real-world problems. Thinking of when you're trying a delivery robot to operate in a city like New York or Tokyo, you cannot use the data collected somewhere in rural Romania, right? So you need this data, well, being representative of the scenarios where your robot will operate. And this is domain gap in terms of real data. In synthetic data, well, it's a difference between real data and synthetic data. And we can have two types of domain gap in synthetic data. The first one is appearance gap. And by appearance gap, we understand pixel level differences to the real sensor output. It can be differences in assets you use to generate your synthetic data, or it can be differences in the capabilities of your rendering systems. The second gap is the content gap. And by content gap, we understand differences in diversity, context, and behavior to real data. That means that, well, something is not fitting in terms of like objects placement, well, this scene is not reflecting the real world. So let me give you an example of context. So many of you might know this example. So the deep learning network has detected there is a tiger. But then you walk closer and you see this. Oops. The context really matters here. And I don't really have to explain this one. Those of you who've ever been to the countryside know that there is no cow which is so long as this. So context really matters. And you may ask yourself, how actually can I breach this sim-to-real domain gap to make synthetic data work for you? Luckily, there are some ways. And basically, to breach the appearance gap, we need to rely on the following. We need to have high-fidelity 3D assets. So the objects you are, well, training on, the objects you create in your data set, they need to be very realistic and close to the real world. You need to have good renderers in place. So it has to be physically based rendering. And the materials need to be also, well, reflective of the real world. You need to rely on validated sensor models, and it's good to consider multi-sensor support. So saying like if you want to generate LiDAR, but also radar data, it's usually beneficial to have the full range of tools supported. And we also need to parameterize the sensors. Like, for example, with a camera, you can have a global shutter, you can have rolling shutter, and it's good to be able to simulate the behavior of real systems which are used to acquire the data. So to generalize the appearance gap, you're striving here for high quality and realism in order to breach this appearance gap. As for the content gap, we need to be cautious of the following. So we need to utilize a large pool of assets. So we need to ensure that the assets are as diverse as possible, which you use. Consider the context. This is self-explanatory. Well, the best way to do it is to have tech and tools to generate new and diverse scenes in place. And it has to be scalable. So you need to be able to generate like not only like 1,000 images, but you need to be able to go beyond that and generate millions of images. And you need to be able to parameterize it and change things quickly. So to summarize this, to breach content gap, you're striving at diversity and extensibility. The technique which helps you with that is called domain randomization. And by domain randomization, we mean varying all these hyperparameters of your data set generation in order to encapsulate the real solution space. So what I'm showing you here is basically a large solution space, which also contains examples which are not necessarily included in the real data. So when generating a synthetic data set, we actually strive at covering a larger set of data, which is not necessarily there. And the idea behind is that by modeling this, we want to make sure that we cover the real solution space for sure. I will show you some examples of that in a moment. So what are the domain randomization techniques? You can understand different things by that, and you can modify, you can vary color or object shape. You can use different lighting, camera placement, and textures and materials, you can zoom in and zoom out your objects, and you can simulate object movement. All these are various domain randomization techniques, and ideally, you want to apply all of them. There are multiple ways to utilize these domain randomization techniques, and the first one is the realistic or minimal domain randomization. That means that you basically create a digital twin of your environment, which looks realistic. And so, for example, in the first example I'm showing you, it's a warehouse, and it looks like a normal warehouse, but we are changing the textures of like the floor, or light is different. There is a daytime and nighttime. Different reflections are also associated with different objects' movement and placement. You can also apply the so-called semi-realistic or moderate domain randomization. So in the animation in the middle, I'm showing you, you all can see it's a room. It looks like a room, but it all has like funky colors and textures, and it looks like as if a crazy person lives there in this room. It's not very realistic, but you can still perceive it as a room, right? And you can also have highly unrealistic and highly diverse scenes with like varying objects overlapping and flying, having weird patterns of movement. So this all, basically the idea behind is that we want to cover all the real-world conditions and encapsulate them in the diversity of synthetic data sets, so that the real world is included in this large solution space, which is not necessarily existent in your data. And this might be helpful, like, for example, unrealistic scenes, like to model shadows or lights or reflections. So this is helpful. You may ask me, which one shall I actually choose? And the thing is, it's all use case dependent, and you might just need to iterate and try different scenarios to see whatever works for your data and for your use case. Here's another really nice example, which I really like. Some researchers published this paper, and they have shown that neural networks, like convolutional neural networks, are very biased towards texture. So in the first image here, you see that the network, which is a typical ResNet 50 classifier, the network has predicted there is an Indian elephant in this image. And, well, looking at that, I kind of agree, yeah, that looks like an elephant. In the image in the middle, the network has predicted, oh, there is a cat there, and we all agree, it looks like a tabby cat. The confidence is a little bit lower than in the first case. In the last image, what they did, they've superimposed this cat image over the elephant texture. And me as a human observer, and well, there's been a study which shows that we as humans, we are biased towards shape. But then when they did that, they've actually realized that the network still predicts that it's an Indian elephant, meaning that the network is biased towards texture. And here is where domain randomization can help you to overcome this texture bias. Meaning that you can take your cat and you can synthetically generate all kinds of funky textures. You can create some crazy colors or crazy, I don't know, like fur textures, and make this network, force this network to explicitly learn the shape of this cat. So this is another good application of domain randomization. What's good as well? You can use domain randomization for testing. You can use your digital twins, and you can test your robots there. Remember, I said that robots need a lot of testing. So you can simulate different environments, and as I also mentioned, falling shelves, you can do it. You're free to do anything in synthetic data. Important to mention here, and that there is also another technique called domain adaptation, which you can also use to generate synthetic data. And I really loved the example from the first talk with generation of this French dish, where Julian was using stable diffusion model for that. So this is an example of domain adaptation, and it's another great way to utilize synthetic data. It's another great way to create synthetic data. In addition to that, you can have all the techniques like GANs, but they're being replaced by transformers, and things like diffusion models are really, really popular these days. You can use these techniques as well. It's not focus of my talk, but I just thought it's really important to mention that so that you can also use that. In the rest of my talk, I'd like to share with you what approach NVIDIA has on to synthetic data generation. And, well, in NVIDIA research, we also work with domain adaptation techniques, but the particular approach I'm sharing with you is relying on computer graphics and CGI to generate and create synthetic data. And the large enabler behind that is our NVIDIA Omniverse platform. And many of you know NVIDIA as a GPU or hardware company. And I always like citing our CEO who says NVIDIA is a platform company, meaning that in addition to all great hardware we have, we also invest a lot in creating software. And we actually have more software engineers than hardware engineers, as a matter of fact. And one such software creation of us is NVIDIA Omniverse, which is basically, we consider it to be a backbone of the metaverse, and you can use it to build metaverses, right? In the middle of Omniverse, we have Nucleus, which is the database and the collaboration engine, which brings together creators of different specialties, like designers, engineers, different collaborators, and they all can work together in Omniverse to create digital worlds and synthetic data as well. Like from the bottom up, Omniverse relies on such NVIDIA proprietary techniques like physics, materials, path and ray tracing, and it all comes with an RTX renderer, and then we also offer a portal, a web portal, where you can work and access Omniverse from whenever in the world you are, from whatever client hardware you have, be it a laptop or a workstation. It can run in the cloud. NVIDIA Omniverse allows you to generate synthetic data. And let's see which extensions of Omniverse help you to generate synthetic data. And the first one, and it's actually not proprietary by NVIDIA, it's developed by Pixar. It's called Universal Scene Description, or USD format. We were thinking, what is the most suitable format to represent virtual worlds and the metaverse? And after extensive search, we decided that USD is basically the most suitable format to create virtual worlds. We consider it to be the HTML of 3D worlds, and we base our NVIDIA Omniverse on this USD format. In the nutshell, it's the open source API and the framework for complex scene graph generators, complex scene graphs creation. You can work simultaneously on the scene graphs, and this has like a really nice feature where multiple collaborators can access the same USD graphs to work on them together. This is a really nice feature of, the USD workflow, where you have multiple layers, and it is conceptually very similar to layers in Photoshop, where you know that each layer modifies a pixel on the screen and how it looks like, and each layer contributes to the final image. Here, there is one major difference, however, is that different collaborators can work on different layers, and they can have different versions of various layers. And then there can be performed some voting where the highest performing layers, they win. But the good thing that all previous versions, they still remain there, and you can have the full history of all versions there. On top of USD, we have our MDL, NVIDIA Material Definition Language. And MDL is open source, and it's GPU friendly. Basically, it has an associated distiller that simplifies shaders for preview in virtual reality applications. Meaning that with MDL, you can generate highly realistic surface textures, you can have reflections, you can have rough textures, you can simulate different materials like metal, glass, plastic, cloth, all sorts of. So the images I'm showing you here have been generated using MDL, and well, it makes basically your scenes photorealistic. On top of that, we have physics simulation. And by physics simulation, we mean things as physics 5 for rigid and soft body and vehicle dynamics. We have physics blast to simulate fracture and destruction, as I'm showing you in the video in the middle. And we have physics flow to generate highly realistic combustible fluids, smoke, and fire. With all these tools in place, you can basically create movie-like scenes, and you can simulate all kinds of environments in a very realistic way. Then we have our Omniverse RTX renderer, which also relies on GPU. It has multi-GPU support, and you can use it to render on the multi-node setting to create the whole world simulation. The images coming out of this renderer are highly realistic. You can simulate also different sensors like camera aperture, field of view. This is all also supported there. And it is based on USD and supports MDL format. And all this comes together in our tool, which is called Omniverse Replicator. And basically, Omniverse Replicator is the dedicated extension of Omniverse, which is designed specifically to enable you with synthetic data generation. In Omniverse Replicator, you can generate scenes like the one I'm showing you in this image, so where you take different assets, and applying domain randomization, you can place them in different constellations to create different highly photorealistic scenes. Let's look at the workflow. How do you work with Replicator? Basically, Replicator has these 3 following components, which are semantic schema editor, where you load your USD schema, and then you can tweak different parameters of your USD models. We have visualizer, which basically is used to show you the scenes which you're generating, but also it can be also used to see the labels for this scene. And finally, we have the replicator core, and let's dive deeper and see what is contained in the replicator core. First of all, it has randomizers, and this is the part of Replicator which is responsible for domain randomization. As I'm showing you in this short video, is that, we have all different kinds of objects aligned on the tabletop, and you can vary number of objects. For each object, you can parameterize that. You can also vary lighting, putting your light source into different parts. You can have mesh lights, you can have dome lights. Those of you who have experience with computer graphics, you may know what it means. And you can control, like, do I want to have more objects on the edges or in the middle? So as a developer, you can actually write your own scripts to operate a replicator. And there is also a GUI in order to control that. So in addition to that, you can write your own scripts. Omnisynthetic data is basically the lowest level component of the replicator core. And it allows you to take the USD data, pass it through Hydra. Hydra is basically the framework from Pixar, which allows you to transfer your USD scenes to the renderer. And then, it comes to the renderer. And with that, you can generate your scenes. You can generate all kinds of labels as sensor data, as I'm showing you in this image. You can see normal maps, segmentation masks, depth labels. It's all coming from there. And we also have replicator annotators, meaning, again, you can generate the segmentation masks, bounding boxes, and it's also customizable and programmable. So if you say, OK, I want to have another kind of labels which are super specific to my application, you can implement that. And on top of that, we have replicator writers, meaning that you, as a developer, are deciding what kind of output you want to have. And as I've already also mentioned earlier, you can have like different networks. They can expect labels in different formats, Kitty, Coco, Pascal formats. We have a set of, well, most of the state-of-the-art formats. But again, you're also free to extend it. And you can use your favorite programming language to do that and to create your annotations in the format your network needs to help. And then you can output it to the cloud, on the edge, to your robot, to the GPUs. So this is highly flexible. Omniverse Replicator today comes in 2 flavors. And for robotics, we have specifically created NVIDIA Isaac Replicator, which comes with some robotic samples. And you can also connect it to our Isaac Gym, where you can actually train robots doing some cool reinforcement learning stuff. And for autonomous vehicles, we have our NVIDIA Drive Replicator, which helps you to generate the world outside and simulate the trajectories of movements for your autonomous vehicles. Here are a couple of resources. So the link to NVIDIA Omniverse, you can find it online. You can just simply Google for it. The Omniverse Replicator documentation, and I highly recommend you checking our technical blog. We often publish there updates on our hardware, our software, and we publish a lot about synthetic data as well. So to summarize my talk, here are the key takeaways. So today I've told you that in order to create robots which are capable of doing useful things, you want them to be fully autonomous. And in order to create fully autonomous robots, we want to rely on AI. AI robots need a lot of data for training, and they need a lot of training and testing. And real data comes, well, which you can use for training your robots, comes with a set of limitations. And to breach these gaps of real data, we want to rely on synthetic data. Synthetic data can help in many different ways. And when you're training your robots with synthetic data, you need to be aware of the so-called sim-to-real gap. In order to close and breach this sim-to-real gap, you need to rely on techniques like domain randomization and domain adaptation. We at NVIDIA work hard to, well, enable you with the tools for that. And I've presented to you our NVIDIA Omniverse, which relies on techniques like PhysX, USD, and MDL to enable creation of synthetic data. And at last but not least, I've presented to you Omniverse Replicator, which is our framework for synthetic data generation.